Hey, welcome back. In this video, I'm going to describe how to take the second derivative of a multivariable function. Back in the good old days of one-variable functions, we only had one way to calculate a second derivative. The way we would do that is we would find f prime, and then we would take the derivative of that to get f double prime. For a function of more than one variable, it's more complicated. We already saw for first derivatives that we have, instead of one different derivative, like f prime, we have f sub x and f sub y, two different derivatives. Turns out that for a function of two variables, and for functions of, this is two variables, not more than one. More than one, if you have three variables, it's different, but for a function of two variables, we'll have four different second order partial derivatives. Those four second partial derivatives are listed here. The first one, the top left, is the double x derivative. You take the x derivative twice. You take the x derivative the first time, and then whatever result comes out, you take the x derivative of that. The other normal-looking second derivative is the double y derivative. You take the y derivative, and then you do it a second time. The ones that you may not have expected to see are the mixed partial derivatives. You start by taking an x derivative, giving you f sub x, and then you take the y derivative of that. That would be this first one, f of x sub y. And then the other mixed partial derivative is you start by taking the y derivative to get f sub y, and then take the x derivative of that to get fyx. The nice thing about the types of functions we'll be working with is that those mixed partials, evaluated at any coordinate or on their own, pre-evaluation, will always be equal to each other. So in other words, fxy is always equal to fyx. This concept of second order partial derivatives kind of growing with the number of variables, you can extend this to more variables. You can extend this to 3 variables and beyond. If you have 3 variables, you have 9 different types of second order derivatives, some of which are equal to each other. See, and then for 4 independent variables, you'll have 16 different types of second order mixed partial derivatives, and you can probably figure out the pattern from there. Some people like diagrams, tree diagrams, for example. Starting from an initial function f of x comma y, you can take 2 paths in terms of first derivatives. You can take the x derivative path on top or the y derivative path on the bottom. And then from those intermediate starting points, f sub x and f sub y, each of those have 2 paths that you can choose from. Either you can take the x derivative of that or the y derivative of that. And the same for the bottom branch, you have 2 different choices. So that's one way to picture the process of taking a second order partial derivative, deciding which branch you want to take along each part of your journey. Also knowing that these two will always be equal to each other. fxy will always be equal to fyx. That equality can be used as a check. If you take the mixed partial derivatives in one order and take them in the other order and you have a different answer, it means either one of your answers is wrong or both of your answers are wrong. So we'll do a mixed partial derivative for this expression. So step 1 is we're going to find the y derivative, the die by die y. We're going to find actually f sub y, I'll write it that way. F sub y is equal to the y derivative, die by die y, of x squared plus the y derivative of y squared minus the y derivative of 3xy. We're going to factor the constants out front, x squared times the y derivative of 1 plus derivative of y squared is 2y minus 3x times the y derivative of y. So we'll get 0 plus 2y minus 3x. So 2y minus 3x. Now we'll take the x derivative of that. F sub yx is equal to the x derivative of f sub y. So the x derivative of the first term, the x derivative of 2y, minus the x derivative of the second term. So factor the 2y out, you have 2y multiplied by the derivative. Oh, I should be a little more careful writing some steps here. So in this step, we treated x as a constant for f sub y. Once we're done that step, x is no longer a constant. X has gone back to being a variable. Now for the next step, or when we are taking the x derivative of that, now y is a constant. So this can get confusing unless you accept the fact that each variable can play a different role at different times. And sometimes it's a constant, and sometimes it is treated properly as a variable. What decides that is the action that you're taking. Taking an x derivative means you're changing the x variable and leaving y held fixed. You're leaving it held constant. So it has no rate of change for that calculation, and it can be treated that way. When we went to the second one, now we will treat y as a variable, y as a constant, for the x derivative. We're going to treat y as a constant and x as the variable. Okay, so I'm going to take the 2y out. I'm going to have di by dx of 1 minus derivative of 3x is just 3. So I'll have 2y multiplied by 0 minus 3. We get negative 3 as the answer. What I invite you to do on your own is to check that fxy is the same. Check if you take the x derivative first. So you get 2x minus 3y, and then take the y derivative of that, make sure you get negative 3, and you do. They'll always agree. Okay, we'll do a set of derivatives here. We want all 4 mixed partial derivatives, mixed second partial derivatives, or not mixed ones, not only mixed ones, all of them. We want all 4 partial second order partials. So we'll start with the first derivative, f sub x. I'm going to take the x derivative of each of those pieces. So 3x squared plus, take the y out front. We have y multiplied by the derivative of x squared, so y multiplied by 2x. It's going to be 2 times xy plus 1. Derivative of 1 times x is 1, and derivative of 4 is 0. Then we're going to take the x derivative of that, and we'll take the y derivative of that separately. So for the x derivative, we're going to have f double x is equal to di by dx of what we just found, 3x squared plus 2y times di by dx of x plus di by dx of 1, and we will get 6x plus 2y times 1 plus 0. So 6x plus 2y. So that's our first one of 4 partial derivatives. Now we'll go to the next one, fyy. or fxy rather. So that'll be die by die y of 3x squared plus die by die y of 2xy plus die by die y of 1. And we'll have 0 from the first term. Since there's no y in there, the 3x squared can be brought out front, and we have the y derivative of 1, which is 0, plus we can take the 2x out front. We have 2x multiplied by the derivative of y, which is just 2x times 1, plus 0, and we get just 2x. So there's our first partial derivative, or mixed partial. That was fxy. Now we're going to start the second branch. We're going to start with the y derivative. Go back to the very beginning, take the y derivative of that expression. So 0 for the first part, plus x squared times 1, plus 0 plus 0, treating x as a constant. So that's going to be just x squared. And then we can take the x derivative of that, and then we can take the y derivative of that. We take the x derivative, so we get die by die x of x squared. We get 2x. Oh, and I should give this the name that it has, f sub yx is equal to 2x. Now that's good news. Those two things are equal to each other. fxy is the same as fyx, which is necessary. They're both equal to 2 times x. Now we take the y derivative of x squared. So die by die y of x squared, and we get 0. And that's okay. That's perfectly fine. Doesn't mean that we made a mistake. Okay, and that's it. Okay, tougher one. We're going to take the four second partial derivatives of this function, and we're going to start the same way. I'm going to start by taking an x derivative branch on top, a y derivative branch on the bottom. So for the x derivative, f sub x, we're taking the derivative of the log of a function, the ln of w. So our derivative is not going to be w prime over w, it's going to be w sub x over w. So on top, we're going to put the x derivative of x squared plus y, which will be 2x plus 0, since y is being treated as a constant, over x squared plus y, which is 2x over x squared plus y. And now we're going to build our two branches. We're going to take the x derivative of that and the y derivative of that to get the second order derivatives. Okay, so f sub x is going to be treating this as a quotient rule, because we have to. This is the top function or bottom function. We will have the bottom function times the derivative of the top with respect to x, so not tb prime, but not bt prime, but bt sub x, minus tb sub x, all divided by b squared. So the bottom function, we have x squared plus y, times the derivative of the top with respect to x, which is 2, minus the top function, which is 2x, times the derivative of the bottom with respect to x, which is 2x plus 0, all divided by the bottom squared, x squared plus y, all squared. And I'm going to leave that alone. I'm just going to not simplify that to save some time. I think something nice happens. You get a little bit of cancellations happening, but it doesn't get particularly beautiful when we're done. So I'm not going to waste time simplifying it. Okay, now the next one's very similar. when we take the y derivative of f sub x, that'll give us fxy. So now for that t and b, we're going to have the bottom function times the derivative of the top with respect to y, minus the top function times the derivative of the bottom with respect to y, all divided by the bottom squared. And then I'll throw in those quantities. So the bottom function x squared times y, or x squared plus y rather, multiplied by the derivative of the top with respect to y. The top is 2x. The derivative of 2x with respect to y is 0. So I'll put a little explanation here for that. Di by dy of 2x is equal to 0. Minus the top function, 2x, times the derivative of the bottom with respect to y. The derivative of x squared is 0. Derivative of y is 1. All divided by the bottom squared. X squared plus y all squared. Now I'll leave that alone. I won't simplify it. Although I should add a little comment here that di by dy of x squared is equal to 0. That's where that 0 came from. Okay, now, well, that's the first branch and our first two partial derivatives taken. Second partials, I mean. Now we're going to do the next branch. We're going to start with the y derivative. So we have ln of w. We're taking the y derivative of that. We'll have w sub y over w instead of w sub x over w. So the derivative of the top with respect to y is going to be 0 plus 1 over x squared plus y. And now we'll do the x derivative of that. Treating this as a t over b. And then below that we'll do the y derivative. Okay, so we will have fyx is equal to bt prime minus t. No, I just did it prime. It's not prime. We're taking the x derivative of what we just found of f sub y. So bt sub x minus tb sub y, or b sub x. What am I doing? Only x derivatives, all divided by b squared. So just a reflex to put the prime, but you have to fight it. Okay, bottom function, x squared plus y, times the derivative of the top with respect to x. The derivative of 1 is 0. Minus the top function is 1, times the derivative of the bottom with respect to x, so 2x plus 0, all divided by the bottom squared. X squared plus y all squared. Now compare that to what you have directly above it. They are identical. So again, fyx is the same as fxy. Okay, now we have the last second order partial derivative, f double y. So there'll be a quotient rule again. It'll be the bottom function times the derivative of the top with respect to y, minus the top times the derivative of the bottom with respect to y, all divided by the bottom squared. Okay, so the bottom function, x squared plus y, times the derivative of the top with respect to y. Well, the top is 1, the derivative of 1 is 0. Minus the top, minus 1, times the derivative of the bottom with respect to y. So the derivative of x squared is 0. Derivative of 1 times y is 1. divided by the bottom all squared. Now that simplifies, but I'm not even going to do that. So there are your 4 second order partial derivatives. Now, last question, starting with an exponential function, take the 4 second order partials. Before taking a derivative, I'm going to identify what type of function this is, what type of big derivative rule applies, and this is an e to the power of w type of rule. So let's start with the x derivative, f sub x. So that'll be the derivative of e to the power of w with respect to x. The derivative of e to the w is e to the w times w prime, but for a partial derivative, it's e to the w times w sub x. For f sub y, it'll be e to the w times w sub y. Okay, now e to the w, so e to the 2xy, times di by dx of 2xy we can factor the constants out front. We have e to the power of 2xy multiplied by, I'm going to take the 2y out front, and we have the x derivative of x, which is going to be e to the 2xy times 2y times 1, which is just e to the 2xy multiplied by 2y. Now we're going to have the second derivatives to do. We can take the x derivative of that, or we can take the y derivative of that. Okay, so taking the x derivative, I'm going to write it out a little more carefully. F double x is equal to the x derivative di by dx of e to the 2xy times 2y. I'm going to factor the 2y out front, since we're treating y as a constant, and we have the x derivative of e to the 2xy, which is going to be 2y times e to the w times w sub x once again. So 2y times, we already did this derivative. We took the x derivative of e to the power of 2xy, and we got e to the 2xy times 2y. And we can simplify a little bit. We can put the 2y and the 2y together. We'll get 4y squared e to the 2xy. Okay, now we'll do the y derivative. So fxy, the y derivative of f sub x. So di by dy of e to the 2xy times 2y. And actually, I'm going to modify this question a little bit. I'm only going to ask for 2 of the mixed partials because it's going to take more space than I realized. Just those 2. So we'll have half as much as the last ones, just for the sake of time. Okay, now we're taking the y derivative of that product of terms. We cannot factor the e to the 2xy out front because it is not a constant, it contains a y. We cannot factor the 2y out front. It is not a constant either because it contains a y. This is where we need the product rule. We have an a and we have a b. So when we take the derivative, we're going to have an a times b prime, but it's not b prime, it's b sub y plus b times a sub y. So it's a product rule. Can't factor anything. Well, we could factor 2 out, but it isn't worth it. So I'm going to do the product rule off to the side. A is equal to e to the 2xy. A sub y is e to the w times w sub y. So e to the 2xy times the y derivative of w, di by dy of 2xy. So e to the 2xy times, take the 2x out front, now the y derivative of y, so we get e to the 2xy times 2x. That's our a sub y piece. And then b sub y is going to be a lot nicer. B is just equal to 2y. So b sub y will just be 2. And we'll plug those in. So we'll have a e to the 2xy times b sub y, which is 2, plus b, 2y, multiplied by a sub y, which we just found, as e to the 2xy times 2x. And then we can simplify. 2e to the 2xy plus 4xy e to the 2xy. Don't take shortcuts, especially not when it's messy like this. We had a product rule, we had derivatives of exponential functions rule. Lots of stuff can go wrong. We had to swap which things we were treating as constants, which things we were treating as variables halfway through the calculation, and that can mess with you. It messes with me. It's just something you have to do carefully. You can't go wild and try to do it very quickly. So that's it for second order partial derivatives. We'll move on to the next topic in the next video.